तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we started a discussion of the MOS field effect transistor. So we shall continue this discussion in this lecture today. In the last class, we covered the fabrication steps and the device structure. We have also given a simple history of how this device has come into importance. Then we explained the symbol and correlated the various components of the symbol to the device structure. In this particular lecture, we will start developing the characteristics of the Mosfet. As we had shown in the previous lecture, our goal is to explain the following characteristics. So the biasing arrangement is shown there. There is a gate source voltage, then there is a drain source voltage. These particular set of characteristics are shown for bulk to source voltage equal to 0. So you see that the substrate or bulk here, bulk to source voltage, this is the source, this voltage is 0. So the characteristics involve drain current versus drain to source voltage for various values of gate source voltage. Now let us see how we can develop these characteristics. So ID VDS characteristics. For this purpose, we will draw the Mosfet in this particular fashion. So this is your p-type substrate, and now the source and drain will be assumed to be top and bottom. So that is, we will assume that this is the source and this is the drain. Now for simplicity, we are showing the source and drain to be very small, okay, and just enough to make contact to the inversion layer. In practice, the source and drain regions are such that you have a depletion layer from both the source and drain region coming into the channel, but that part we will not discuss in this particular first level theory of the transistor. Here you have the oxide layer and this is your gate. Now an important point to note is that when you want to develop the current voltage characteristics starting from the device physics, then it is convenient to use the bulk as the common terminal. So though in practice the source is shown to be the common terminal, to develop the characteristics we will use bulk as the common terminal and then transform these voltages to the voltages when you use the source as the common terminal. That means the following: we will use this as the common terminal and then we apply a voltage to the gate with respect to the bulk so as to create the inversion layer here. So you have the inversion layer here. Then we apply a voltage to the source with respect to bulk. Now in our characteristics this particular voltage has been shown to be 0, but that is the characteristics on the slide, but here we will have an equation which will also take into account this voltage, then we will set this voltage equal to 0 to see how the equation simplifies. So this is VSB. And then we have the drain to bulk voltage. VDB. Obviously the VDB is more than VSB, only then this will be called the drain, because then the electrons will move from here to here, or the current will be from here to here. So whichever terminal is more positive is called the drain for an n channel transistor. So whichever n plus terminal is more positive. So here we are considering n channel device. Now once we derive the ID as a function of VGB, VSB and VDB, we can always convert these equations to the form when source is the common terminal. This can be done as follows. You see that VDB for example is equal to VDS minus VBS. Similarly, VGB is equal to VGS minus VBS, and VSB is equal to minus VBS. Now our approach here will give us ID as a function of VDB, VGB and VSB. Then we will substitute these equations here, okay, and the same equation then can be written as a function of VDS, VGS and VBS, okay, these are VBS. So that is the outline of our approach which will be used to find out the characteristics. It will become clear when we discuss the charge picture inside the device what is the advantage of using the bulk as the common terminal. When we do that, we will be able to write the equations for various charges very easily in terms of the physics that we have developed for the MOS capacitor. Now let us look at the charge picture in the device. How does it look like? Now notice that when we don't have any difference between the drain to bulk voltage and source to bulk voltage, that is when VDB is equal to VSB, then the charge will be uniform because everywhere the potential is the same. So you will have the inversion layer and you will have the depletion layer under the inversion layer or next to the inversion layer. Of course we are assuming that gate to bulk voltage is more than the threshold voltage of this capacitor for this particular source to bulk voltage, okay, so including the body effect. So VGB is greater than VT, which is of course a function of VSB, because otherwise you will not have any inversion layer. So that is what we will assume. So to start with, when VDB is equal to VSB, your picture is like this: a uniform inversion layer charge and a depletion layer next to the inversion layer, which is also uniform. VGB is greater than VT so that the inversion takes place. Now to pass a current through the inversion layer, you will change the VDB to a value more than VSB. So when you make this more, then this picture is going to change, because the voltage along the channel now is going on increasing. from VSB at the source to VDB at the drain. Now what is the effect of increase in voltage on the channel? Clearly if the voltage on the channel increases, the voltage difference between the gate and the channel decreases as you move up. Now let us set up a coordinate system. So this will be our x axis and this will be our y axis and this will be our origin. So you vary the distance from 0 to x in this direction and 0 to y in this direction. Now we are considering the effect of applying a VDB more than VSB. Let us now define a channel voltage Vy at any point y. So this is Vy, this is the channel voltage. Now how does the channel voltage change? Vy is equal to VSB at the source and VDB at the drain. Please note that all voltages are referenced with respect to the bulk. So Vy is the voltage between this point, channel here, and the bulk. Now obviously when Vy is changing, your depletion layer will not be uniform and your inversion charge will not be uniform. Now we want to determine how the depletion and inversion charges change. So first let us write down the value of Vy. So Vy increases with y and its values are Vy is equal to VSB at y is equal to 0 and it is equal to VDB at y is equal to L, where capital L is the channel length. So this distance is denoted as the length of the channel L. The width is the distance in the perpendicular direction. The width of the gate is in the direction perpendicular to this. So it is something like this. If you take this perpendicular direction, then that is the width of the gate. Now coming back to the effect of variation in the voltage along the channel on this particular charge, inversion charge and depletion charge. So as Vy increases, VGB, that is the gate to bulk voltage, minus Vy, which is the voltage across the oxide, that will go on reducing as you move in the y direction. Now if the voltage across the oxide reduces, obviously the total charge, that is inversion plus depletion charge in the substrate, will decrease. This follows from the parallel plate capacitor analogy. So charge on any plate or electrode depends on the potential drop over the oxide. We have discussed this in the context of MOS capacitor. We have also discussed this in the context of body effect. So since the total charge here will decrease, but since the voltage drop across the inversion layer is increasing, because increase in Vy, obviously voltage drop here is increasing, the depletion layer has to expand. So the depletion charge should increase as you move in y direction. So in other words, this is a MOS capacitor with a changing body effect from source to drain. So the body effect is increasing from source to drain. So total charge should reduce, but depletion layer charge should increase. So inversion charge should definitely reduce as you go from source to drain. So as your body effect increases from source to drain because of change in Vy, increase in Vy, the inversion charge will reduce and depletion charge will increase. So we shall show this as follows. So inversion charge is something like this. So this shows the decreasing inversion charge, and at the same time you have an increasing depletion charge. So the depletion layer is shown to expand. So this is the charge picture in the MOSFET. Now based on this charge picture, we must derive the current voltage characteristics. So now we will show a simplified diagram showing only the variation in the charges in the MOS capacitor, and see how when you change your drain to bulk voltage, the current goes on increasing, but then after some time it saturates. So for this purpose, let us draw a simplified diagram as follows for different drain voltages. So this is your substrate, this is the inversion charge, and this is the depletion charge. So this is for one value of VDB. So this is VDB1. Now for another value of inversion charge, another value of voltage VDB2 greater than VDB1. So this is the p-type substrate. We are not showing source and drain, it is understood this is drain and this is source, and of course you have a gate on this side. So maybe we will just show the insulator. So for VDB2 greater than VDB1, your picture would be as follows. Notice that the charge at the source will not change because your source to bulk voltage is not changing. Only the charge at the drain will become even less because the voltage is more. So something like this. So this charge at the drain is less than this charge. So but this depletion layer is wider. So at the source it remains the same, but at the drain it is wider. So this VDB2 greater than VDB1. Now clearly from here, if you want to show the current variation, it will be as follows. So we are drawing ID as a function of VDB in this case, and this point is VDB equal to VSB when the current is 0. So you start from here. Now we can assume a simple resistor model, and we can say that the current flowing, that is the ID that is flowing in like this, is given by the voltage drop across this resistor. The resistor is formed by this inversion layer. Voltage drop across this resistor, which is VDB minus VSB, divided by the average resistance of this particular inversion layer. That will give you the current. So let us say that current is something. So initially you had 0, as you increase your VDB you get current. This corresponds to VDB1. This is ID1. Now what about ID2, that is the current flowing here. Now the average resistance of this region has increased because the charge at the source is the same, but the charge at the drain here is less than this. Since the mobile charge that can participate in conduction is less at the drain here than in this case, on average the charge available here for conduction is less than this charge. Since the charge available is less, obviously the resistance is more. So now supposing the VDB2 is such that VDB1 minus VSB is same as VDB2 minus VDB1, suppose it is an equal increment. Then for the same increment, the increment in the current however will be less than ID1, because the resistance of this region is more than the resistance of this, okay, and that is because on average the charge has reduced when you increase the drain to bulk voltage. So that being the case, your current will increase, but it will increase, the increment in the current here will be less than the increment ID1, something like this. Okay, so this increment is same as this increment, but this increment in current is less than this increment because the average resistance has increased. So therefore your current tends to reduce, the increment in the current tends to reduce, okay. That explains why you are getting a curve like this which is non-linear, okay. It is an increasing current, but it is increasing at a decreasing rate as you go to higher and higher drain to bulk voltage. Now a point will come when for some value of VDB the charge here will become 0, the inversion charge which is going on reducing as you increase your drain to bulk voltage will become 0. So that will be something like this. So this is your inversion charge and it has become equal to 0 here. So this is ID3. And this is VDB3 greater than VDB2, and of course your depletion region will be even more, so something like this. Now for this case it can be shown that after this, even if you increase your drain voltage, the amount of charge here cannot reduce because already it has become 0. So therefore what will happen is that beyond this point it can be shown that the current cannot really change significantly. If you increase your VDB further, the current cannot change. Now how it cannot change, that we will shortly show. Let us show this point on the graph here. So something like this. This is VDB3. Now notice that VDB3 minus VDB2 is not necessarily VDB2 minus VDB1. This is some voltage to which you come when the charge becomes 0. So here inversion charge is equal to 0. That is the voltage VDB3. Now let us explain why the current cannot change much beyond this point. If you increase your voltage beyond this point, the charge picture will look something like this. So you have a region delta L here, this is L, channel length, over which the voltage beyond the voltage VDB3, that is what we showed here. For voltage VDB3, the inversion charge becomes 0 right at this point at the drain. Now your voltage is VDB4 here, greater than VDB3. So over this delta L you have a drop VDB4 minus VDB3. So here the situation is as follows. This is delta L, so your voltage falling across this delta L here region is VDB4 minus VDB3, the extra voltage beyond VDB3, and the voltage VDB3 is falling here. So this voltage is VDB3 and this is the zero inversion charge point. So the zero inversion charge point has shifted away from the drain a little bit closer to the source, okay, by a value delta L. So we can therefore say the channel length has now become equal to L minus delta L. In other words, you have what is called channel length modulation. Which we shall abbreviate as CLM. So now what is happening is that over the length of the channel equal to L minus delta L, you have a voltage drop VDB3, and since delta L is really small, what is happening is the picture here for VDB4 greater than VDB3 is almost same as the picture for VDB3, the charge picture. So even when you change the voltage, the drain voltage, your charge picture is not changing significantly, okay. Therefore the current picture does not change much. In fact, there is a very small increase in current because the resistance of this is a little less than resistance of this, simply because the length here is L, whereas the length of the resistance here is L minus delta L, right. This resistance, this distance is L minus delta L. So because of this delta L, the resistance decreases a little bit and therefore the current increases to a very small value. So that is why beyond this, if the delta L was not there, then it would have been just constant, but in practice it will increase slowly. So that explains how for a given gate to bulk voltage your current changes as you change your drain to bulk voltage. The current starts increasing, but the rate of increase decreases. Okay, so therefore the slope of the curve is decreasing because the average charge in the channel goes on reducing, though your drain to bulk voltage is increasing. So ultimately at some point the charge, inversion charge becomes 0 at the drain. So this corresponds to the condition when Qi at y equal to L, QIL is equal to 0. Now this point is normally referred to as saturation point. Because beyond this point the current almost saturates, though not exactly. It does not saturate totally because of the channel length modulation. So here this region is normally referred to as the so called ohmic or sometimes even linear region, though it is not exactly linear. In fact, only a very small region here near the origin is linear, but still sometimes people refer to the entire region as linear or ohmic region, and beyond this you have the saturation region. So the nomenclature of saturation is different in bipolar transistor and MOS field effect transistor. So MOS field effect transistor saturation is really referring to the active region of the current voltage characteristics, whereas in bipolar transistor saturation is the other than active region, that is before the active region of the current voltage characteristics. Now these terminologies mean different things in bipolar and MOS transistors because people who have been involved in development of the theory of the bipolar transistor and the MOS field effect transistor have been different. So different people have developed the theories for the two transistors. That is why the nomenclature means different things in the two different cases. Now to complete the qualitative analysis, before we take up writing the equations, we must explain what will happen to the current voltage curve if you change your gate to bulk voltage. Now if you change your gate to bulk voltage, obviously the saturation point will also shift. So we would like to know, supposing you increase your gate to bulk voltage, what way will this point change on the current direction and on the voltage direction. Now this is what we will see next. Now evidently when you increase the gate to bulk voltage, your inversion charge will increase. Now the question is, what will happen to the saturation point? Let us look at this charge picture here. Supposing there is a charge picture for one value of gate to bulk voltage. So we are drawing the charge picture at VDB 3, that is when this device is saturated. VDB 3 is the saturation point for say VGB 1. Now you have increased the gate voltage to VGB 2, gate to bulk voltage. Evidently this point here where the charge was 0, the charge will no more be 0, it will increase, it will go beyond 0. So now if you want to push this charge condition to 0, evidently you will have to increase the value of VDB 3 to reach the saturation point. So therefore what we gather is that for higher value of VGB, the current at saturation will be higher and the saturation voltage also will be higher. So this point will shift up and to the right, so something like this. So this is your curve for a higher value of VGB. So as your VGB increases, your curve moves up like this and saturation point shifts to the right. Now what happens to the slope of the curve beyond saturation. When we derive the equation, it will be clear that for higher value of current the slope also will be more. So this slope here is more than this slope here for this curve. Okay. So this slope is more, and in fact if you were to push all these lines back in this direction, then it can be shown they will all intersect at one point on this graph. The voltage axis, they will all intersect at one point. In other words, if I compress this graph, then it would be something like this. So in fact, the way to draw the saturation and the ohmic region characteristics clearly is as follows. So qualitatively, if a student is asked to sketch the drain current versus drain voltage characteristics, this is VSB here, we are taking the bulk as the common terminal. The current voltage characteristics will look something like this. So we first draw a set of lines like this, all starting from one point, each of which represent the current in the saturation region for different gate bulk voltages. Then we separate the ohmic and the saturation region. So these are your points and these are your curves in saturation, and then we join these to get the complete curve. This is very much like what we did for the bipolar transistor. The only difference being that this region in the bipolar transistor is very narrow, whereas here it is much wider, this ohmic region. In fact, that is why the Mosfet has several applications where it is operated in the ohmic region, whereas you do not have any such applications for the bipolar transistor. Okay? So in the ohmic region the Mosfet is used as a voltage variable resistor, because as you can see from here, when you change your gate bulk voltage, the resistance which is shown by the slope of this curve goes on changing. So when you increase the gate bulk voltage, the slope is more, that is the resistance is less. To complete this analysis, let us do one more thing. How will the current change when you change the source to bulk voltage? So far, if you look at the diagram, we have seen the change in current with drain to bulk voltage and with gate to bulk voltage. Now what happens when you change the source to bulk voltage? Now clearly, let us look at this diagram here. When you change the source to bulk voltage, keeping gate to bulk and drain to bulk voltage same, the current will decrease because of increased body effect everywhere. So the charge at the source, inversion charge at the source will reduce, but the depletion charge will increase. Now what is of interest to us is the inversion charge, because that carries the current. If inversion charge decreases at the source, it will decrease everywhere, and so the resistance will be more and the current will be less. Therefore, for increased bulk to source, source to bulk voltage or source to bulk reverse bias, your current levels will be lower. So what we have drawn here, this is a graph for one value of VSB. If you want to draw for another value of VSB, then each of this line for a higher value of VSB will be lower. Now, how will the saturation point change with the source to bulk voltage? This point we will discuss when we derive the expression for saturation voltage as a function of gate to bulk and source to bulk voltages. Next we will derive an equation for the current voltage characteristics. Now for this purpose we will use a simple diagram shown here. So this is our inversion charge changing from source to drain, and this is the depletion charge changing from source to drain. So any point y, you can take a small element dy, and the voltage over this element dy we can assume to be constant. So the channel voltage here at this point is Vy. Now we will try to take this small element and then write down the expression for current as a function of voltage for this element. Then we can do an integration and then get the picture for this total device. We are following this approach because as you can see the charge is continuously changing from source to drain. So by analyzing a small element and then integrating we can get the total picture. Now what are the equations that will be used? Recall what we said in the procedure for device analysis lectures, that any device can be analyzed using the 5 basic equations, that is the 2 transport equations for electrons and holes, the 2 continuity equations again for electrons and holes, and the Gauss's law. We have already shown how using this we can derive the equation for p-n junction and for bipolar transistor, which is based on p-n junction. One can also show similarly in a rigorous manner how starting from the 5 basic equations you can derive the current voltage characteristics. However, we will not follow the rigorous approach because here the picture is 2 dimensional. You can see that you have an electric field that is applied in the y direction and you have an electric field along the x direction. The x directed electric field is from the gate to substrate, the y directed electric field is from the drain to source, which enables you to pass the current. So therefore in a Mosfet the picture is actually 2 dimensional. So you will have to write all those 5 equations, that is the transport equation, the continuity equation and the Gauss's law in 2 dimensions, and then you will have to make approximations and then show how you can reduce a 2 dimensional situation to a 1 dimensional situation. Now this process is mathematically a little bit involved. We will avoid this thing in a first course. However, we will roughly show how the equations are being used. So for example, if you take the transport equations, we neglect the equation for holes because in a n channel device the inversion layer is because of electrons and the hole concentration in this inversion layer is really very small. Therefore, as far as the transport equation is concerned, we are concerned only with the electron transport. So one of the equations drops out. Now further, in the equation for electron transport you have 2 terms, that is the current because of diffusion and the current because of drift. We shall neglect the current because of diffusion. Please note, why can there be a current because of diffusion? Because your electron concentration is changing from source to drain. Therefore obviously there is a tendency for diffusion, but then when your gate to bulk voltage is more than threshold voltage and this region is strongly inverted, it can be shown that the drift current dominates over the diffusion current. Therefore, your transport equation further simplifies to only electron drift. So here we will write transport equation is electron current much more than hole current, and further drift current H is much more than diffusion current. This means that current is because of electron drift. So current solely due to electron drift. Now let us take the continuity equation. Again, we need to consider only the continuity equation for electrons, because holes are out of the picture. The electron continuity equation here will reduce to the following statement, that is, that if you take the current across any cross section, please note that when you take the cross section will be perpendicular to this particular board. You take the current flow across any cross section, that current will be the same along the y direction, and therefore it will be equal to the drain current. So that is a statement of continuity equation. So continuity equation is Iy, that is a current across the cross section of the channel at any y is constant with y, and therefore it is equal to the drain current Id. Now we are left with the Gauss's law. Where do we use the Gauss's law? The Gauss's law is required to express the charge concentration here in terms of the gate to bulk voltage, because that is a capacitor action. So when you want to express the charge concentration in terms of the voltage, you will encounter again in this case a two-dimensional field and potential distribution. So that two-dimensional electric field or potential distribution has to be approximated to one-dimensional distribution to simplify the analysis. This simplification of a two-dimensional distribution to one-dimensional distribution is termed as a gradual channel approximation in the context of Mosfets. So we will first write down what this approximation is and explain it. So Gauss's law. So Gauss's law is, in this case, two-dimensional picture. So dou Ex by dou x plus dou Ey by dou y is equal to rho by epsilon, where rho is the space charge including the depletion and inversion charges. So please recall here what is the x and y direction. The x direction is in this direction. So electric field from gate to bulk, that is the x directed electric field, and the field from drain to source, that is a bidirected electric field. So what we are saying here in this formula, dou Ex by dou x plus dou Ey by dou y equal to rho by epsilon is rate of change of x directed electric field in the x direction plus rate of change of y directed electric field in the y direction is equal to rho by epsilon. That is, we can show it as follows. If you take a volume in the substrate near the surface where you have the electric field, okay. So this volume is taken from here, so you are choosing the volume somewhere here. Okay. So for this volume, what this equation says is, this is the x-directed electric field going in and coming out, this is the y-directed electric field, so actually this is Ey and this is, since y, the field is in this direction but y is upward and x is this way. So this is Ey and this is Ey plus delta Ey or dEy. Similarly this is Ex and this is Ex plus Dex. Now this is dx and this is dy. Now in this direction it is dz. What we are assuming is that the dz or the width direction, the fields are not changing, okay. So therefore actually we can neglect changes in that direction. So we can make this simple and we can show it like this. So now you see what this equation says is the change in the electric field here, that is this increment dEx by this dx plus the increment dEy by this distance dy, and this is rho by epsilon. Rho is the space charge here. The approximation we will make is that we will assume dou Ex by dou x is much greater than dou Ey by dou y. Rate of change of field in the x direction is much more than rate of change of field in the y direction. This is the so called gradual channel approximation. With this approximation what will happen is, this equation, this quantity will become negligible. So you will have dou Ex by dou x is approximately equal to rho by epsilon. Let us understand why this mathematical equation should be called a gradual channel approximation. The reason for this is, what we are assuming is that the electric field is not changing much in the y direction as compared to the change in the x direction. Please note that the electric field is changing definitely in the y direction and in the x direction, but the rate of change of the electric field in the y direction is much less than the rate of change of field in the x direction. If you calculate the fields, you will find that the y directed field will be much smaller than the x directed field. A simple estimate can be done as follows. You know that the oxide thickness is less than 0.1 micron, okay. The channel length of the device, however, is of the order of a micron, okay. Nowadays of course it has decreased, it has come to submicron levels, but to make a simple calculation, let us take these values. So oxide thickness T naught is suppose 0.1 micron and the channel length L is suppose of the order of 1 micron. Now gate to bulk voltage is suppose about 5 volts. Let us assume drain to source voltage is also 5 volts. Now clearly the field in the x direction is approximately gate to bulk voltage by T naught. This is approximate order. Whereas the y directed electric field will be of the order of Vds by L. So if VGB and Vds are equal, we assume for simplicity, definitely since T naught is 10 times less than L, Ex will be 10 times more than Ey. In other words, the fields in the x direction tend to be higher than the fields in the y direction. Similarly, one can show by a more involved calculation that the rate of change of field in the x direction will also be much more than the rate of change of field in the y direction. That is equivalent to saying that your channel conditions are not changing very rapidly in the y direction. That is the meaning of a gradual channel approximation. The gradual channel means a gradually changing channel in the y direction. So with the help of this gradual channel approximation, the charge, that is the inversion charge which participates in the current, can be calculated using the one dimensional analysis that we have done for the MOS capacitor. This is the great advantage. So though the charge is changing with y, at any y you can use a one dimensional approximation and find out the charge in terms of the voltages there, and then you can put the change in voltage and that will give you the change in the charge concentration. So that is the approach of simplifying a two dimensional picture to a one dimensional picture. So in summary, the 5 equations are used as follows: transport equation, no hole current and only drift current for electrons. Continuity equation, again no hole current and the current is constant with y, that is the statement of continuity equation. And Gauss's law, you assume that the picture is really one dimensional, that is in the x direction from gate to bulk, and based on that you find out the amount of charge. This is the so called gradual channel approximation. Now putting these results together, we will show in the next class how an equation can be derived for the charge as a function of voltages at any element dy at a distance y, and how you can integrate the result from source to drain to get the complete current voltage equation.